Hi, in this video, I am going to talk about principal component analysis and its efficiency in summarizing the state of an economy at a given month, and with this, its role in predicting monthly GDP. We are going to start with the inspiration of this project. Then we're going to talk about what is a state of an economy, particularly that of the US. And then we're going to talk about principal component analysis and its role in understanding the state of an economy. Lastly, we'll talk about monthly GDP predictions using stochastic gradient descent. What inspires this project is how a computer reads a digital image. A digital image is made up of pixels. Say a square image, it can be made up of n by n pixels. Here is a picture of a deer. Zoom in close to its ear and you see little square pixel that represent grayscales and colors and how the computer should interpret it. Look far away and we see and we perceive a photo from a human point of view. Now, one can view the economy as the same way. Given an image of an economy at a given moment in time, it can be identified with by its various indexes and other scales. For example, one can view the Standard and Poor 500 stock index and interpret how the financial market is operating. We can look at the manufacturing output and see how its level of production is going. And from here, collectively, we can see how the economy is operating. Thus, given all of these indexes together, we can view the state of an economy. Hence, when looking at each of these individual indicators, we are taking the computer approach to understanding the economy itself. And now, what we need to do is to be able to interpret all of these indicators entirely, looking far away to see what is the economy telling us, what is it showing us, like that picture of the deer showing us. As said, a picture of an economy is made out of many indicators, and these indicators can be political, demographic, educational indicators. They don't have to necessarily be economic indicators. It gives us the entirety of the image of the society and its economy. Now, one question you might wonder when collecting data for this project is, how do you manage to get only monthly data? Well, dealing with data frequency was one of the biggest challenges of this project. We asked, how are we able to convert weekly data into monthly data and then quarterly data into monthly data? For example, the unemployment insurance claim is a weekly data, and a GDP growth rate or a GDP level is a quarterly data. We only want to obtain monthly data. So given the two ends, the weekly and the monthly, we use Pandas library called resampling to interpolate monthly data. And with that, we obtained throughout our entire data set only monthly data. A note here is that when dealing with quarterly data, we are making up some data points because those data points were not available to us for all the 3 months that a quarter covers. So what we use a technique that economists tend to use, traditionally have been using, which is called a cubic spleen interpolation, and that allows for a more accurate interpolating of data, making of data given only quarterly data. The data set comes from the Federal Reserve St. Louis, and the guidance as to which indicators to pick come from the Organization of Economics, Cooperation and Development. In total, there are 679 monthly observations available from January 1960 to July 2016. Any months out of this interval do not have complete data set for this project. Each monthly observation has 100 features, which are 100 dimensions, and the labels come from quarterly real GDP that have been cubic spleen interpolated to monthly real GDP. To understand why we use PCA, we need to understand the characteristic, the nature of these independent variables. So we have 100 features, which are 100 dimensions. We do not know which one of these have the biggest impact or sufficient impact and which one has the least impact on GDP. In addition, there are correlations among these dimensions as well. For example, the industrial production index are influenced by the manufacturing output, and the consumer sentiment index is influenced and influencing S&P 500 index. So now we use principal component analysis to identify patterns in our data to detect correlations among variables, amongst dimensions. If a strong correlation exists between any two variables, it's natural to reduce this dimensionality to reduce redundancy. How PCA works is that it finds the directions of the maximum variance in high-dimensional data and projects it onto a smaller dimensional subspace while retaining most of the information of the data, thus improving computational efficiencies. So we have 100-dimensional data. We would like to project this data set, onto a smaller subset. And the key benefit is that we obtain projected data that are linearly independent. That means there's no correlations among independent variables, and also that computational efficiency has been improved. Note that PCA is not feature eliminations, as we are using all the features and data provided, not dropping any one of them that we think are important or not contributive enough to GDP. So PCA is a technique of features extraction such that we use to create new independent variables, one that is a combination of the existing ones, and they are all independent of one another, and they summarize our data set. The procedure for PCA starts with standardizing and normalizing data because each of our features has different units. Then we obtain a covariance matrix that is symmetric and provide the covariance among different features. From there, we seek for eigenvalues and their corresponding eigenvectors, which we use to construct a projection matrix to transform our data that we use for our machine learning algorithm. In this particular case, we use it with stochastic gradient descent to predict GDP level. Now that we have obtained the eigenvalues and their corresponding eigenvectors, we can see that the first eigenvalue and its corresponding eigenvector explains about 62% of the variance of the data. The second eigenvalue with its corresponding eigenvector explain about 10% of the remaining variance of our data. And from here, the variance explained gets smaller and smaller as the value of eigenvalues decreases. That means we can drop all the smaller eigenvalues and their corresponding eigenvectors. With this, the first principal component is a linear combination of original predictor variables that captures the maximum variance in the data set. It determines the direction of the highest variability in the data. The larger the variability captured in the first component, the larger the information captured by the component. No other component can have variability higher than the first principal component. The second principal component is also a linear combination of the original predictors that captures the remaining variance in the data set and is uncorrelated with the first principal component. Thus the correlations between the first and the second component is 0. From this plot, one can see that the first component analysis explained the most variance of the data by itself, and the second principal component bears only about 10% of it, and it gets gradually smaller as the number of principal components increases. Thus, we can see that our projection matrix simply just needs 6 eigenvectors to be able to summarize about 90.3% of the variance. We will use this projection matrix to transform our data from 100 features, 100 dimensions to only 6 dimensions, improving efficiencies and allowing that all of them are linearly independent. Using the transform data set that we obtained, which is now only 6 dimensions, we apply stochastic gradient descent to predict GDP. The predicted result over the observed result give an overestimation of about 7.2%. Here, we can see that applying PCA, we make sure that our variables are independent of one another and at the same time reduce the dimensions of the data to avoid overfitting due to dimensionality and reduce computational complexity by increasing computational efficiency. Reduce the number of dimensions in our feature space. PCA allow for extraction of subspace that best describe our data and hence improving computation in machine learning algorithms.